Well, welcome back, and we're going to try and explain Rescorla Wagner today. And more importantly, I am going to try and explain to you why this is a really cool model and it is actually really theoretically important. So we'll see if we can do that. And we'll see if we can share this. And I think we've got it sharing my screen. And now, of course, they're going to bark in the snow and the whatever, but that's okay. And rather than trying to go full screen, I am going to go this way because it's far easier than trying to make it go big right now. Because every time I try and make it go big, I seem to have it stop doing it. Bella? No. Thank you. So, the Rescorla-Wagner model is a model of prediction that tells trial by trial when the predictability of an event is going to happen and how much learning is going to be supported by that situation. So, there are obviously a number of theories of classical conditioning and why we respond to predictability. And we can kind of rule out, and we've talked about the fact that it is not simply that the CS substitutes for the US, and therefore the CR is simply a substitute for the UR. Rather, it does seem to be that the UR is different somehow than the original unconditioned response. We know that we get compensatory responses. We also know that even the salivation that was formed during the unconditioned stimulus is not the same as the salivation we see during the conditioned stimulus. There were some suggestions that maybe the animal just doesn't pay attention to cues that aren't related to the US. And we know that it's not that the animal doesn't pay attention to unrelated cues, or remember, those are cues that are unrelated to the unconditioned stimulus and therefore doesn't form responses to them. The animal does indeed see the stimuli, but doesn't use those stimuli as predictive. Kamen came along in the late 60s and suggested that animals pay attention to stimuli which require mental work that predicts the unconditioned stimulus and therefore the unconditioned response, and that the animal has to be surprised that they continue to learn as long as there is something more to learn, that the animal has to continue to do mental work. And you reach asymptote when the animal no longer has to do mental work. And so then along, there's a great theory. And the thing is, Kamen is right, but he didn't have a way of computationally showing that. And so this is where the Rescorla and Wagner computational model came along. Now, this model was written originally in 72 and then again in 74, a slightly revised model came out. It still works today. It is still a very good model today. And I think that that is really important to understand, is that it is indeed a very good model. It's certainly been tweaked. And I would hope that any model that was written in 1972 has certainly been improved upon in 2021. So that's true. And our current attentional models that are the more modern models, more modern versions of Rescorla-Wagner are there. All they have done is slightly revise the computational model and I think kind of nailed down some of the explanatory assumptions that Rescorla and Wagner tried to make. Other than that, the model is still very much true today. So again, we know that Kamen's work in 1967 through 74, with his blocking and overshadowing work, demonstrated differential learning to differential stimuli. And yes, Pavlov talked about this, but Kamen was the first one to really talk about this in terms of prediction, and that the causal mechanism seemed to be the predictability or the ability of the CS to predict the US. And in overshadowing, you get one weak and one strong compound CS. So one CS seems to be more salient or stronger than the other CS, and conditioning seems to occur differentially to them. So you get a stronger conditioned response to the stronger CS and a weaker conditioned response to the weaker CS when you test them individually. So you train them together and then you test them individually and you get these differential conditioned responses. By the same token, if I train one predictive CS to a US. So I've got a light that predicts shock, and I train it to asymptote. I get a very good CR to it. But now if I add a second CS to it, so I've got a light and a tone, and it's the same unconditioned stimulus that's predicted by this compound CS, I don't get any increase in the strength of the conditioned response. And this is true. And again, if I test light, I get great avoidance. But if I test the tone alone, I get little to no avoidance. So we could argue that the light that was the original learning blocks the learning that would occur during a compound stimulus. So I don't even get the overshadowing effect. I just get nothing. So that it seems to be that light was the only predictor, even though obviously the tone is absolutely 1.0 predictive here, but it's just not learned to, so to speak. And this is demonstrated by Kamen. And Kamen suggested that this was because the animal didn't have to do any additional mental work when the tone was added. It didn't add anything to the situation, but he couldn't explain this theoretically. So the Rescorla Wagner model was born. And this is a trial-by-trial learning model that says the change in learning that occurs in any given trial is due to a constant times the amount you can learn, or the amount of conditioning that can be supported by a CS-US conditioning situation, minus the amount you've already had learned. Now, to make this constant a bit better, they modified it to include the salience of the CS and the salience of the US times the amount supported by that CS-US relationship minus how much you've learned. So V sub I is the amount learned on any given trial. Alpha sub I is the salience of the CS. Beta sub J is going to be the salience of the US. So lambda sub J is the amount of conditioning that the US supports to that USJ. And then V sum is the amount of conditioning that you've already done. So again, here we read it again. And let's put that in English. The amount of conditioning that will occur on any given trial is a function of the size of the salience of the CS multiplied by the size of the salience of the US, multiplied by the maximum amount of learning that can be supported by the CS-US relationship, minus the amount of learning regarding that CS-US relationship that has already occurred. So we can say it easier. How much we learn on a given trial is a function of how good a stimulus the CS is, how good a stimulus the US is, how much learning can be learned about the CS-US relationship, and how much you've already learned. There you go. English is much better. Although, you have to admit, that looks cooler. Okay, so like any model, there have to be some assumptions of the Rescorla-Wagner model. And again, this is a learning model as opposed to a performance model. And we'll use many more performance models later on. But right now, we're going to assume that we're going to have a learning model here. And it's going to predict the amount of learning between the CS and the US as it occurs trial by trial. And so we have to assume that the animal can perceive both the CS and the US, and that the animal can make both the UR and the CR. We're going to assume that it's helpful for the animal to know two things about conditioning. First of all, we want the CS to predict the type of event that is about to come, and then we want that CS to be able to predict the size of that event. Is it a little shock or is it a big shock? Is it a shock or is it a steak dinner? I want to know those things. Right? Am I going to get a bite of steak or am I going to get the whole steak? So classical conditioning is really learning about the signals, which are predictors for important events. And so we're going to learn how good these signals are and respond to the signals depending upon how good a predictor they are for that important event. So again, we have to have a few more assumptions. We assume that with each CS-US pairing, the CS might be more inhibitory, more excitatory, or have no change. How? Well, if the US is larger than expected, the CS is deemed excitatory. So if I was expecting $100 and I got $200, I would go, oh, the CS predicts $200 in this situation. If the US is smaller than expected, so again, I'm expecting $100 and I only got 50, that would be inhibitory, right? So now that CS predicts $50. It no longer predicts the $100 that I was expecting. And if I got $100 because I was expecting $100, yep, there's no change. So the effect of the another important part here is that the effect of the reinforcers or non-reinforcers on the change of the associative strength depends on not only that CS, but of all other stimuli currently present. So if there is a better predictor than my given CS in my experiment, the animal should attend to that better predictor. And this basically suggests that the animal attends to the best predictors of the upcoming event. And that could be one predictor, that could be multiple predictors. And those multiple predictors could be ranked based upon how good each of those predictors are. So we have to have some idea of how the animal is doing this. So Rescorla and Wagner assumed that there had to be some direct brain link between the CS center and the US center, much like Pavlov suggested. And they were suggesting the development of a neural circuit. And I said, okay, there has to be some neural circuits because we were just starting to learn about neural circuits about this time. And of course, the other learning theorists thought Rescorla and Wagner were absolutely nuts, but it turned out that they were absolutely right. And there are indeed not only neural circuits, but even on a cellular level, we can demonstrate the change in this case, dopamine as a predictor neurotransmitter. So that's going to become a very important aspect of Rescorla-Wagner models. Now, we can also assume that the strength of an event is a given. The strength of a 1 milliamp shock doesn't change. So therefore, the amount of learning that it can support is set. That's a constant. The CS is not necessarily constant, and that's what's changing, is how good a predictor that CS is to that constant US is what's being learned. Now, more modern models will argue that event, the predicted event, is not necessarily a constant. It may indeed vary depending upon other situations. But right now we're going to focus on the CS side of it. And so Rescorla-Wagner model is really doing it the CS side and not the US side. So when learning is complete, the strength of association relates directly to the size of the intensity of the CS, and the asymptote of learning is the maximum amount of learning that can occur to the size or intensity of that CS. The maximum amount of learning that a given CS can support as predicting a given US. We also are going to assume that the change in associative strength of the CS as the result of any given trial can be predicted from that composite strength of all the stimuli. And this is where we can look at things like overshadowing. And the composite strength is a summation, the kind of additive bits of all the stimuli that are there. And we know that if the composite strength is low, my lambda is high, like my lambda is 100, say. I'm going to set my 100. 100 units can be learned. And if I've only learned 2 things, that leaves a lot more learning. That leaves 98 more learning events that I can learn. And on a given trial, more will be learned. But if I've already learned 98 out of 100 units in that situation, there's only 2 left that can be learned, and the amount of learning on a given trial is going to be less. So the more there is to learn, the more I can learn on a given trial. And as there's less to be learned, I learn less on a given trial. And that's simply describing that asymptotic curve, the fact that the curve starts off steep and slows down as it approaches asymptote. All right. We can also expand this to extinction or non-reinforced trials so that we can look at the extinction curve where I stop having the CS predict the US. And what happens then is that associative strength is weakened. We get an inhibitory effect. And by the same token, initially, the first time that CS doesn't predict the US, that's a lot to be learned about that relationship, and I'll get a huge drop. So the extinction curve drops off quickly and then levels off kind of in the reverse version of this composite strength of the asymptote, starting out steep and slowing down. Again, the extinction curve starts out steep and slows down just because it's more of an inhibitory curve. But notice that extinction is not the stopping of learning. You learn extinction just like you learn the original CS-US prediction. You're learning the CS doesn't predict during extinction. It is indeed learning in and of itself. All right. So why is this important? Because we can make 3 rules about the direction and amount of classical conditioning. If lambda, the amount I can learn about a CS-US relationship, is greater than V sum, I get excitatory conditioning. The degree to which the CS predicts the size of the US was greater than expected, you react more to the CS on the next trial. If lambda is less than V sum, I get inhibitory conditioning. So if I could have 100 units of learning and my V sum is already 100, well, there's no change down here. Or if my lambda is 100, but now the CS is predicting 110, well, I react less because it's not equal to my lambda. The degree to which the CS predicted by the size of the US was less than expected means that I react less to the CS on the next trial. And again, if they're equal, I get no change. I get no learning. There was no learning to be had. So let's use this to explain learning, overshadowing, and blocking. And again, remember that this equation is going to be the amount learned for a given trial depends on the salience of the CS, the salience of the US, and the amount you can learn minus the amount you already have learned. All right, got all that? Let's put this baby to work and we'll try a few examples. So, acquisition. Our first conditioning trial, assuming all of our givens, we have a CS of a light and a US of a 1 milliamp foot shock. So when the light turns on, that means shock is coming. How much have I learned? What is my V sum on trial 1? Well, I've never seen this before, so my V sum is 0 on trial 1. And let's assume that my lambda, how much I can learn about this particular CS-US relationship, is going to be 100. Why? Because 100 is a nice number to work from. Easy to calculate. So 100 minus 0 equals 100. So how much can I have to learn? I have 100 units I can learn. But will I learn all 100 units? It depends. It depends on the salience of the light and of the shock. So we're going to make it a perfect light and a so-so shock. So let's plug it in to the equation for trial 1. The amount of learning on trial 1 that I do is 1 for my salience of my light, 0.5, that's the salience of that 1 milliamp foot shock, times 100 minus V sum, which is 0. So 0.5, right? 1 times 0.5 is 0.5, times 100, because 100 minus 0 is 100, equals 50. So the amount of learning on trial 1 approaches 50% of the discrepancy between what I can learn and what I have learned on the first trial. I learned 50 conditioning units on that very first trial. Hot dog. All right. Trial 2. I'm going to plug it in again. My lambda, or my alpha and my beta have not changed, but now my lambda is still 100. But what's my V sum on trial 2? I have to take it forward, move it forward from the trial 1, so it's 50. So 0.5 times 50 is 25. I learned 25 conditioning units on the second trial. And after my second trial, what's the total amount I've learned? 50 from the first trial plus 25 from this trial. So my V sum is now 75. Because again, I'm bringing it forward after each trial. So I go to trial 3. How much will I learn on trial 3? Well, my alpha and my beta haven't changed, but now 100 is how much I can learn. 75 is what I've had learned. Just 25 units left to go. So 0.5 times 25 is 12.5. What's my V sum? So this is what I've learned on trial 3. But now after trial 3, how much have I learned? I have learned 50 plus 25 plus 12.5, which equals 87.5 units of learning on trial 3. On trial 4, I plug it in again. My alpha and my beta haven't changed. My lambda hasn't changed, but now I've got 87.5 from V sum. So 0.5 times the 12.5 I have left to learn is 6.25. And what's my V sum? 50 plus 25 plus 12.5 plus 6.25, which is 93.75 units of learning I've already done by trial 4. By trial 10, my V sum is 99.81. And about trial 14, I reach 100 going out 5 or 6 decimals. Now, theoretically, when will I reach asymptote? Well, if I can go out infinity decimal points, how long is it going to take me to reach my maximum amount of learning? Well, by definition, infinity. But realistically, at some point, we're going to say, nope, 2 decimal points is plenty. And I'll say by trial 10, I've reached asymptote. All right? But technically, you never, ever learn everything you can learn about a situation. So there. So let's graph this. Here on trial 0, I knew nothing. On trial 1, I learned 50 units. Trial 2, my V-sum is 75, 87.5, and so on as I go out. But look at how much I'm learning on each individual trial. My V sub I is smaller because it is almost the inverse of this relationship. Because there's less to learn, because I'm getting towards 100, there's less to be divided up for each of those trials. But again, theoretically, I'm never going to completely reach asymptote, and I'm never going to theoretically stop learning. Realistically, yes. Theoretically, no. But now you can see this is how we actually get the real learning curve. And now I have actually shown you I can predict trial by trial how much a rat should learn if I know the salience of the shock, if I know the salience of the light, and I know about how much my asymptote is going to be. I can see, well, I predict asymptote should be about here. This is when it should level off. I test the rat. I actually look at his condition suppression ratios and see, and by George, this is what I get. And we do fits to the curve. We look at the animal's actual curve in comparison to our theoretical curve and match them on top of each other and see to what degree the curves are equal. And we get fits to the curve at about 9. Our R-squareds are about 0.95, if not higher, in the laboratory situations. Obviously not real life situations, but in laboratory situations, using a Rescorla Wagner model, I can predict with R-squareds of about 0.95, which is pretty cool. You don't see that very often. All right, so now let's go back and use this to explain blocking and overshadowing. Again, overshadowing is one weak and one strong. More learning occurs to the stronger stimulus. Blocking is you learn to the first, I add a second, and you don't seem to show any learning to that second additional stimulus. So let's figure out how do we explain overshadowing first. And yep, it's good old Rescorla Wagner to the rescue. So again, Pavlov talked about this, and he used a compound conditioned stimulate, a light and a tone, or whatever you want to use. One is intense and one is weak. And after a number of trials, he found that you got a strong CS. With the stronger CS elicited more CRs, stronger CRs, where the weaker CS elicited weaker no CRs. And even though this occurred, even though you presented them at the same time and you presented them from trial 1. So why should one overpower the other? And of course you go, well, because one's stronger than the other. Well, we know that, but they didn't know back in the 70s. And we had to demonstrate it both theoretically and in actual data and see if our theory matched our data. So let's use Rescorla Wagner to see if we can explain why. We're going to assume that the light has a salience of 0.2 and our tone has a salience of 0.5. But now our shock, that's our B is our shock, for the light and the tone is going to have the same salience because our US is a constant. So only the light and tone differ in salience. The shock is the same shock predicting them both because it occurs together. Now, what is our V sum on trial 1? It's 0. We've never learned anything. But we have to calculate learning to each CS. So to the light, we go 0.2 times 1. That's the salience of our shock. Times 100 minus 0 because we haven't learned anything. So I learned 20 conditioning units to the light. But remember, our salience of our tone is 0.5. So now 0.5 times 1 times 100 minus 0 is 50. So I learned more to the tone than I did to the light, about 2.5 times more. And what's my V sum? My V sum is the combination or the additive of both of these. So I learned 20 to the light, I learned 50 to the tone, I learned 70 conditioning units about that CS-US relationship in total. Trial 2, I have a VL, right, my light on trial 2, 0.2 times 30 I've got left over is 6. 0.5 times 30 is 15. So now my V sum is 70 plus 6 plus 15 is 21. So it's 91. Trial 3, I plug it in again. I only get 1.8 to the light. I get 4.5 learning units to the tone. And my V sum after trial 3 is 97.3. So I'm reaching asymptote much faster with the compound CSs, but they're not, each conditioned stimulus is not taking up an equal amount of those conditioning units. In fact, at asymptote, the CS of the tone would take up 70 units, where the CS of the light would only take up 30 units, because the CS of the tone is 2.5 times stronger. 0.5 is 2.5 times stronger than 0.2. So we see this differential sharing of the amount of units that the two CSs take up, even though they were presented together. The bigger one overshadows the weaker one. And we can demonstrate this again by making a graph. Here's my light. Didn't learn much. Here's my tone. But if I add these together, I get my V sum, and I get quite a bit of learning to the compound CSs, but the learning is not shared equally to each individual CS. Isn't that cool? And again, I can play with the rat with this. I can give the rat the compound learning. I can test each one. And if I've done it right, the learning to the compound stimulus should equal my V sum. And I should get conditioned responses that equal what I'm predicting to the tone and equal to what I'm predicting to the light. And if I'm right, I get fits to the curves with R squareds of about 0.95, and I go, yes, Rescorla Wagner is indeed right. So blocking is going to be almost an exactly similar situation, all right? Only now we have to remember what V sum is going to be. So it doesn't matter what the salient of the light or the tone is. In fact, I'm going to set them equal, okay? I'm going to put them equal in a second. And the idea is that the CS has practically absorbed all the associative strength that can be supported by that CS-US relationship. My V sum is at asymptote. At asymptote, how much more is there to be learned? 0 is the correct answer, right? So I trained to CS alone. I trained to the light alone, and I've reached asymptote. Okay? I did 100 trials of the light, and now I'm getting a very strong conditioned response to the light. And now I go into the second part of the experiment, and I have a CS of the light and a salience of the tone, and I do them together. How much is left over to learn to this additional tone? Nothing. Let's make this math easier. So what am I going to get here? My V sum to the light is 100. What's the V sum to the tone when I do light tone trials? It's 0. Yeah, there's no learning that can occur. And I can demonstrate this. Okay? I can plug it in. It doesn't matter. Okay? I can take 0.464 times 1. Okay, so 0.464 times 1 is 0.464 times 100 minus 100. Well, 0.64 times 0 is 0. I can't learn anything. The tone, when I added it, didn't add anything to the situation because the light already did perfect prediction. So how can I eliminate this blocking effect? Oh, I can do it very easily. I'm going to mess with the lambda. I'm going to change the US to a 2 milliamp shock. And that's going to increase the amount of learning that can occur to this situation to 160. I've added a change, okay? So V sum is still 100. I've learned 100 units to the 1 milliamp shock to the light. So the light is indeed predictive of a shock, just a 1 milliamp shock. And now when I add the tone, the shock is a 2 milliamp shock. Will I learn to the tone? Yes. So let's assume the light and the tone are equally salient. So now on trial 101, because I've already done 100 trials to the light, I do 101 trial, 0.2 salience of the tone times 1 to the shock. That's going to be my salience, times 160 minus my V sum of 100. Well, that's 60. So 0.2 times 60 is, I learned 12 units to the tone. And if my light had the same salience, I learned 12 more units to the light. Now, the light now takes up 112 learning units, and the tone only takes up 12 units. I may get some overshadowing here, but I learned to the compound. As long as the light and the tone occur together, I'm learning about it because there was more learning left. I raised this to 160. My V sum was already 100. I have more learning that can occur. And my V sum after trial 101 is now 124. And if I do it on a trial 102 here, second trial of the compound CSs, I have V sum of 124. And again, 7.2, 7.2, 138. And again, I've got a monotonically increasing curve. By altering the lambda that the US is able to support and changing it, it changes the amount of learning that CS US learning can support. And so now the tone and light predict a 2 milliamp shock, which is bigger than the 1 milliamp shock predicted by just the light. And I can show that there's going to be a difference. Yeah, lights predict shock, but lights plus tone predicts the bigger shock. And so the animals learned kind of differentially that way. So here we go. The Rescorla Wagner model. Looks real fancy. V sub I equals alpha sub I times beta sub j times parentheses lambda sub j minus V sum on parentheses. But what does the equation say? The equation simply says that the amount of conditioning that will occur on a given trial is a function of the size of the salience of the CS multiplied by the size of the salience of the US multiplied by the maximum amount of learning minus the amount of learning that has already occurred. Pretty cool. You can say this much easier. How much you learn on a given trial is a function of how good a stimulus the CS is, how good a stimulus the US is, how much can be learned about that CS-US relationship, and how much you've already learned about it. Cool. So, based on all the head tilts, I'm guessing that you'll want to have this explained to you again. But we're not going to do that now. Don't worry. But what I do want you to think about is here we're using with the CS of the shock, the light or the tone, and the shock is the US. We're using suppression ratios and the change in responding between no shock and shock conditions, and therefore the CS and no CS conditions. What dependent variable might I use if I am doing this as an advertising agency and I want to measure behavior for going to McDonald's? Obviously, I can't show my logo and then shock you, because all I'm going to do is I'm going to make it an aversive logo instead of a appetitive logo that I'd want. So what would I use as a dependent variable? How would I measure how good that McDonald's logo is? What would be the behavior I'd be looking for? And by the same token, let's say I'm going to do some systematic desensitization, and I have a dog who's afraid of men. The CS of men in that dog's life has predicted bad things, and I want to make that CS extinction. So I'm going to either present lots of men with no fear happening, or better yet, I'm going to replace it. So now the CS of a man predicts steak instead of fear. What kinds of dependent measures would I look for in that dog? What would be my dependent variable that I'd be measuring to see that indeed the dog no longer found that CS as predictive of a bad thing and instead found that CS predictive of a good thing? And these are the applied problems we have, is what kinds of measures can we use? And of course, then the other question is, are those the only CSs in the room, so to speak? And are those the most predictive CSs? And that's tough to say. That's always hard to say. We just hope that our CS, our intended CS, is always the best, and there isn't something else sneakily taking up more of the variance. So let's take a look back here again. And I hope you've had a good time kind of understanding Rescorla Wagner. I know that it's not the most fun thing to do, but it's probably, especially when you start talking about the neuro end of it, one of the most compelling, one of the most predictive models, and one of the coolest models I think I've ever seen. Not my research area, I admit, but I absolutely love this model. And if I didn't find classical conditioning research boring, I would probably do this. So I think that's enough for now. We'll talk about this more on Thursday. And again, really think about what would you look at for advertising, for systematic sensitization, for other kinds of classical conditioning. What would be the dependent variables you'd use? What might be some competing conditioned stimuli that you might worry about? And how can we use this out in the real world? And this is going to tie into some of our drug discussions we have, discussions on how CSs can really play havoc with drug effects. And I will talk to you soon.